Good evening, students. Unit 4, Chapter 6, Chemical Periodicity. This is Part 2. Let's look at a little bit of review from what we did last class. Classification of the elements. We have found that on our history, Mendeleev arranged the elements according to increasing atomic mass, but had a few issues. Moseley, who had come after we discovered the proton, arranged the elements in order of increasing atomic number, and that is the modern table that we use. Therefore, periodic law, the definition of this table is when the elements are arranged in order of increasing atomic number, there is a periodic pattern, a cyclical, there's a cyclical repeating of physical and chemical properties in each group. Remember, groups are the vertical columns on your periodic table. Okay. The periodic trends, we find that when we look at a periodic table, we can also determine properties that repeat or do something as we move across the table, get bigger, get smaller. And so this arrangement of the periodic table provides us with a general idea of certain periodic trends. We're going to look at those trends, and you are responsible for the trends that are in bold-faced and underlined print only. The first trend is effective nuclear charge, and that is given the symbol or abbreviation ZEFF. This effective nuclear charge is the pull that the nucleus exerts on the electrons. The larger the effective nuclear charge, ZEFF, the tighter the electrons are pulled and the smaller the atom. So the trend on my periodic table for effective nuclear charge, or ZEF, is highest at the top right of the periodic table. And we're going to put this on our flip chart, this trend in our flip book. Question. Which elements in the following pairs would have the highest effective nuclear charge? And the highest effective nuclear charge, if this is my periodic table, it would be highest at the top of the table to the top right. So we're going to point toward the top right. Magnesium or chlorine? Magnesium is found right here on my periodic table, and chlorine is found right here on my periodic table. They're on the same period. So who has a higher effective nuclear charge? Who's higher to the right-hand corner? Chlorine is. Rubidium and strontium on the periodic table. Rubidium is in the first group down here at the bottom, and strontium's in the second group on the same period. And I'm having difficulty with this because it doesn't seem to be calibrated. And so I'm going to pause for just a second and calibrate the board. Okay, now it appears to be calibrated. So if I'm looking at this first box that's in green, that is my element rubidium. And the second green outline is strontium. Which one's closer to the right-hand top corner? Yes, strontium is. And so our answer to that question is strontium. Aluminum or astatine? Well, aluminum and I'm going to use my white symbol, is right on the crooked line on my periodic table. And so aluminum is located right here. And I'm going to put it in white. And astatine is down here toward the bottom of the periodic table. Which one's closer to the top right? That would be aluminum. And so aluminum is our answer to that question. All right. Periodic trends, and now we're looking at atomic radius as a trend. Atomic radius is 1/2 the distance between the nuclei of two like atoms in a diatomic molecule. And so we're looking at the trend. This is how they measure it. They take chlorine that is attached to chlorine, and they measure the distance between those two nuclei. That would be atomic radius. And 1/2 of, excuse me, 1/2 of that distance would be atomic radius. So from here to there would be an atomic radius. The more energy levels present, the larger the atom's going to be, because it's going to force those two nuclei farther apart. When comparing atoms that all have similar energy levels, the atoms with the largest nuclei, and thus the greatest number of protons, will have the smallest radii. The guys who have the biggest nucleus, the most protons, they're going to be the smallest in size because their powerful nucleus is pulling the outside electrons in. And so the trend we find for atomic radius is that it increases from left to right and from top to bottom. So we're going to draw on our flip chart when we get doing flip chart. If this is our periodic table and we're drawing the trend, the atomic radius increases from right to left. It gets bigger as you go that way, and it gets bigger as you go down. So what we're pointing to, where the largest actually are, is at the bottom left. That means bottom left would be the largest in size, and top right would be the smallest in size. And so we're going to do that in our flip book in class. There's our trend. Here's our periodic table looking at them. We're going to put it in again. Atomic radius increases as I go down and increases as I go to the left. So the biggest one is francium at the bottom, and the smallest one would be helium at the top right. Place the following elements in order of increasing atomic radius. So we're working in with those elements on our periodic table. So I'm going to draw a periodic table. I want to remind us of the trend. The largest is down here at the left. And so we want to show where these particular elements are on our periodic table. And so calcium is right about there on our periodic table. And carbon is right about there. Ra, that is radium, is down here on the periodic table. And bromine is over here on the periodic table. So we know that the largest one is going to be down here in this area of the table, and smallest is going to be the right corner. Then let's put them in order of increasing radius, which means we're going to start here and we're going to move our way down that way. So who's highest? The highest one is carbon, so carbon would be first. Who's next? Well, bromine's to the right. It's lower, but it's on the same level as calcium, and so bromine would be next as we move toward the other side. So calcium would be third because it's higher than the radium, and the one that's farthest down and to the left is radium. We've now put them in order according to the periodic table. That was your margin question. Periodic trend for ionization energy. Well, definition of ionization energy is that it's the energy required to overcome the attraction of the nuclear charge and remove one electron from a gaseous atom to form an ion. That should be one electron from a gaseous atom. So ionization is pulling one electron away from any atom. And the first ionization would be to pull the first electron away. The second ionization would be pull a second electron away. And third, pull a third one away. So if I'm looking at a Bohr model of something like lithium that has 3 protons and it has neutrons in the nucleus, it's sitting on the second energy level, and so I know there are 2 electrons in the first energy level, and there's 1 electron out here in the second energy level. If I'm going to pull one away, I start farthest out. This would be, when I remove that electron, would be my first ionization energy. Second ionization energy would be to remove one of those 2 on the inside, and third would be the final electron that I could pull away. Trend for ionization energy is that it increases as we go from left to right, and it increases as we go from bottom to top. And so if this is our periodic table, a basic square, we're going to have more as we go from left to right, and we're going to have more ionization energy as we go from bottom to top. So my highest ionization energy would be up there in the right-hand corner. We're going to put that in our flip book when we're in class. Let's move on and finish working on the notes. The question that's in the margin: what electron do you think would be the easiest to remove, the first, second, or third? Which one would have the least amount of energy? Well, if I draw my lithium again, with 3 electrons in the nucleus and neutrons in the nucleus, and my electrons are out here, which one of these 3 would be the easiest one to remove? Hopefully that you said the one that's farthest from the nucleus. And so the one that's farthest from the nucleus here would be that one, the one that's in the second energy level. Why? Because it's farthest from the nucleus, and so the protons aren't holding it as strongly. So the one, I guess I should write this in white, farthest from the nucleus would be easiest to pull away, and that's because the protons can't hold it as strongly because it's so far away. All right. Moving on to place this trend on our periodic table again. This is increasing ionization as I go to the right and as I go from the bottom to the top. So my highest ionization energy would be up there at helium. Next trend, ion size. Ion size is, well, what is an ion? An ion is any atom that has gained electrons or lost electrons. There are 2 types of ions: anions and cations. A cation is one that has gained electrons. It's going to be larger and it's going to have a negative charge. So I'm going to highlight that. It will be larger than the original, and it will have a negative charge because it has extra electrons, and electrons are negative. Cations are those that have lost electrons, and they are going to be smaller than their original because they lost some of their electrons, and they're going to take on a positive charge because they've lost some of their negatives. The trend for ionic radius increases from left to right and from top to bottom when I talk about ion size. And so if this is my periodic table again, and I'm following the trend as I go from right to left, and as I go from top to bottom, my ion sizes are going to increase. So this is ion radius will get bigger as I go down. So my biggest will be at the bottom, just like it was with the atomic radius. The ion radius does the same trend. Largest at the bottom left. Okay, so here is that picture again. Increasing radius as I go down and increasing radius as I go to the left. That means that my largest ion radius will be at francium and my smallest ion radius will be up there at helium. So on our periodic table, we can use a periodic table to be able to answer these questions of trend. What is larger, an atom of nitrogen or its anion? And so nitrogen is 7 protons in the nucleus, and we're going to go ahead and put 7 neutrons in the nucleus. It has 2 energy levels because it's sitting on the second period. It has 7 electrons, and those electrons, the first 2 are in the first energy level, and the rest of them, 5 more, are sitting in the second energy level. Draw them as negatives because they're electrons and they have a negative charge. So this is a normal atom. What would it look like if it was an anion? Going back to the definition of an anion is an atom that has gained an electron. And so, if this has the same size nucleus, and it has, there's my atom with 5. Well, what happened to this one? This one gained another electron. So instead of having 5 on the outside ring, it has 6. This guy is going to be larger because I have an extra electron in that ring that the protons are trying to hold in. And because of that, anions are going to be larger than the original atom. Our last trend in the notes is electronegativity. Electronegativity is the tendency of an atom of an element to attract electrons when they are chemically combined with the atoms of another element. So if sodium is combined with chlorine, they're forming a bond. Can this chlorine attract another electron to itself? So we're looking at how able it is to attract another electron to itself. Noble gases don't have any electronegativity because they're full. They can't attract any more electrons to themselves. And so for this particular trend, the noble gases don't have any. If I draw a periodic table, I remember that the noble gases are in this group. They don't have any electronegativity, so we don't write or use anything with the trend for them. But our trend is as it goes from left to right and from bottom to top. So as I go from left to right and from bottom to top, it's getting more. Well, it can't be anything in the noble gas. And so our highest element is going to be fluorine. Fluorine has the greatest electronegativity. Our least electronegativity would be down there at francium in our left-hand corner. Francium would have the lowest electronegativity. So fluorine can attract electrons to itself even when it's bonded, but francium would have difficulty doing that. So let's put the trend up here on the periodic table again. Increasing electronegativity goes toward the top right corner, but none of the noble gases have electronegativity, so they would not be in this trend. That means our highest would be fluorine. Question in the margin. If hydrogen and fluorine make a bond, which atom would have more bonded electrons near its nucleus? So hydrogen is bonded to fluorine. And which one has higher electronegativity? Hydrogen is on the left-hand side of the table and fluorine is on the right. So this one has a higher electronegativity. That means that it can attract more electrons to itself. And so that means that more of the electrons in the bond would be near the fluorine. Fluorine would have the higher amount of electrons in the bond and in the atoms to be attracted to its side because of the high electronegativity of fluorine. And that is the end of our notes.